Right, students. So now we will try to understand different instances where objects are at equilibrium under two forces. So to understand that, first I have a metal ball here and also a wooden block, a block of wood. So what we will do is we have a Newton balance here. You are familiar with that, and you all know there is a spring there which helps to get the reading of the Newton balance. So this particular spring has a certain tension. Now initially look at the length of the spring. It is a certain length. So accordingly there is a certain tension. Now if I hang this object, the metal cube there, observe what happens to the spring. So here you can also get the reading of the Newton balance. At the same time, you were able to observe that the spring stretched a little bit. So with the stretching of the spring, what happens to its tension? It increases. And also you all know, students, for any object, there is the mass acting along with the gravitational acceleration. Due to that, weight is acting on the object downwards. So the downward force acting on this metal ball is its weight. And the upward force that is pulling the metal ball up is the tension of the spring. And they are in opposite direction. Tension is upwards, the weight is downwards. And the magnitudes are equal. Because of that, the object is at rest. Is that understood? Is that clear to you all? So the object is at equilibrium, or this is known as the equilibrium of two forces acting in opposite directions but along the same line of action. The same way, now if I replace this ring with the block of wood, now can you all see? The spring stretched even more. Why? The weight of the block of wood is higher, so that means the downward force is higher. In order to balance that, the spring stretched more, exerting a higher force upwards. So according to the weight of the object, the upward force, that is the tension of the spring, changes. So that means the downward and upward forces are equal and opposite in direction. So then the wooden block or block of wood is at rest and there is equilibrium between the two forces. Is that clear to you all? The same way, I will take off the block and I will take off the Newton balance as well. If we directly now hang this, normally you all know there is no tension for the thread. But if we hang this with the weight that you all know, now can you see? You can feel the tension here. Why? The weight is acting downwards but the object is at the same height. So that means it's not moving. So to balance that downward force of weight, there is a tension acting upwards along this string. So since the object is a small object, a small weight, the tension is somewhat small. The same way, if we use this wooden block, I will have this and with the same thing, the same way if I hang the wooden block. Now here you can see both the objects are hanging down. So the weight of the object is downwards and as I told you before, there is a tension here. If you were doing this activity, you can feel the tension in this string as well as this string. You will understand there is more tension here. Why? The weight is more, so the downward force is more. Therefore, to balance that, there is a higher tension acting on this string. Whereas here, less weight, less force upwards. The tension is less. So now do you all understand? So both the objects are at rest or under equilibrium. The objects are at equilibrium under two forces. Downward force is weight and the upward force is tension. Is that clear to you? And these are objects that have been suspended from a support. Okay, students. So now we are going to do this activity to understand the equilibrium of a body under two forces. So for that we have this metal ring here and I have the 2 Newton balances that are used to apply the forces. So as you know, now the ring is at rest. It is at under equilibrium. There are no forces. You know the weight is acting and the perpendicular reaction, all that you all know. But the sideways, now here this is a horizontal surface. Although you are supposed to keep it on the table, I have used another small box here so that you can easily see the Newton balance readings and all that, and also forces can be in the same plane. So you all have to observe whether the threads are in one line. So that means if they are in one line, that means the two forces are acting along the same line. And also you all can see I'll be pulling the Newton balances in the opposite direction. So that means the forces are going to be in opposite directions or opposite forces, but the magnitudes we will try and see whether they need to be equal or different. So initially, if I just pull with one balance, you can see the ring moves. If I pull with the other balance, again you can see the ring moves. So that means there is only one force. Then if we apply, let's say 0.5 Newton here, and I am applying more force on this one. So there again you can see the ring moving. If I reduce this balance, that is on my right side, I make it to 1 Newton, I increase the force here. Now can you see? It's moving to the left side. So when the forces are not equal, that is the magnitude of forces are different, obviously the object will move. But if the two forces are equal in magnitude and in opposite directions, now let's say I am applying 1 Newton force from both balances. Now 2 Newton force from both balances, 3 Newton force from both balances. So now you can see the object is at equilibrium. So there, the line of action that is along the same line and they are in opposite directions, the magnitude is the same. So then the object was at equilibrium. Let's say we will move this to a different direction. Now I will move it like this. Now if I try to pull it again with the same now you can see it falls off the block. So that means it is not at equilibrium. Even if I move it to a different angle, still you will see now here again that's moving off. So that means if you want to keep an object under equilibrium, under two forces, then the forces have to act along the same line of action like this, and they need to have equal magnitude. Is that clear to you all? And also in the opposite direction. So that is the condition that needs to be satisfied. Opposite direction, equal magnitude along the same line of action. Then the object will be at equilibrium under two forces. Okay students. So now we are going to do this activity to understand that when an object is at equilibrium under two forces, you all already know they need to have equal magnitude and they have to act in the opposite direction. They have to be opposite to each other, and also the line should be the same. Line of action should be the same. So then only the object will be under equilibrium. So to understand this, again we have a block of wood, and to that you can see two hooks have been connected so that we can easily connect the Newton balances from either side. And then if I apply equal forces, as you can see I am applying 1 Newton force, 1.5 Newton force from both the balances. Now again 3 Newton force, still you can see the block is not moving. But if I apply just more force from one side, so let's say if I apply 1 Newton from this balance, I am going to apply 1 Newton force, and from this I am going to apply 3.5 Newton force. So can you see the block is moving? Now again I'll apply 1 Newton from this balance that is on my right side. At the same time I will increase the force in this balance. Now can you see the block is moving towards my left side. So that means when the magnitudes, although the forces are in opposite direction, the magnitudes are not equal, means the object will not be at equilibrium. So from that observation also, students, you can clearly understand for an object to be at equilibrium under two forces, they have to be opposite in direction, they have to act along the same line of action, and also the magnitudes have to be equal. Okay, students. So now we are going to observe the equilibrium of an object under three coplanar parallel forces. So you all know what coplanar is. All the forces have to be on the same plane. And parallel, if you take the line of action of the forces, they have to be parallel to each other. So for this activity, now here you can see I have two stands and the Newton balances hanging from the two stands. And also I have a ruler here. We were supposed to use only the meter ruler, but the weight of the meter ruler was very less. So to increase the weight a little bit, I have attached another small wooden plank here that you can see. So then what we are going to do is I have measured the weight of this wooden plank as well. It is to 300 grams, that is 3 Newton. So then now I have two rubber bands here. What we need to do is we need to put the two rubber bands to two ends. Now here I am putting it at the 99 centimeter mark. The same way I will be putting it to the 1 centimeter mark here. So 1 centimeter from this side and 1 centimeter from this end. After that, we have to suspend the ruler from both the Newton balances. So what will happen? The weight of the meter ruler will act downwards, that is in the middle, and the tensions acting along the rubber bands will be upwards. All three forces have to be parallel. That is what we need to observe. And also you have to look at the reading of the balances in order to understand whether the sum of these two forces are equal to the weight of this ruler as well as this particular plank. So here I am going to hang it from both sides. Right. Now we will have to allow it to come to equilibrium. So students, can you all see the two readings? You all can see that the Newton balance here shows 1.5 Newton and the balance here again shows 1.5 Newton. So the total value is 3 Newtons and that is equal to 300 grams. So as I told you all before, the weight of the ruler with the thin wooden plank attached to it is 300 grams or 3 Newtons. So now you all can understand the weight of the object acts downwards from the center downwards, and here the two forces, though, that is the tension and that is what you read in the Newton balance. So sum of these two forces is equal to the third force. All three are parallel, this one and the other force, and the sum of these two forces that are acting upwards is equal to the force that is acting downwards. So now can you all understand the concept? I will repeat that again to you all students. You can see the Newton balances are there and the rubber bands attached to it. So the weight of the object acts downwards, that is one line of action, and the two other lines of action are from the Newton balances. They are acting upwards, and the sum of the two Newton balance reading the upward forces is equal to 3 Newtons, that is equal to the downward force. So these are three parallel coplanar forces and the object is at equilibrium. Now let's say we push this object like this towards the side. From one end, if we push it to a side, you can see there is a movement. At that time, you might see there is a slight change in the Newton balance. But once it settles down again, it will come to equilibrium. So still it is the same reading. Even if we push the object downwards, again it moves up and comes back to equilibrium. So whatever the movement you try to do, still it comes back to equilibrium. That is when the three forces are parallel and in the same plane. So three coplanar parallel forces and the object is at rest. So that means there is equilibrium of forces. Is that clear to you all, students? So from this activity, you all can understand when an object is at equilibrium under three coplanar parallel forces, two forces have to be in one direction, the third force has to be in the opposite direction, and the sum of the two forces that are acting in the same direction will be equal to the third force acting in the opposite direction. So those are the three coplanar forces. Okay, students. So now we are going to illustrate the factors necessary to maintain an object under equilibrium under the action of three coplanar forces that are not parallel. So do the activity, we need a lamina. When we say lamina, it can be a metal sheet like this or else it can be a cardboard. That is very even so that you can hang it like this and you can find the center of gravity first. Then you use that to find the way the three forces that are not parallel acting on the particular lamina. So start the activity. I have made three holes here. You can see here one, another one, and the other one is going to be this point. So I will be hanging the lamina from those 3 points individually, and when it comes to equilibrium, when it is hanging like this, if we place a ruler along the line of the thread, we will get a straight line. Like that, we can draw the lines and you will see how they intersect each other. So here students, you can see along this twine string, you can see there will be a line. So to get that line, we will have to hold the ruler like this and get the lamina to come to equilibrium. And then if you place the ruler, so now you can see string. So we will have to draw the lines there. So this is going to be one line. You can see here. Then what we will be doing is, we will have to remove the twine and then I will have to tie it at a different point. So do this again. We will have to find the line of action. Again, if I hold the ruler like this, you can see this is going to be the line of action. So that's the second line. Then again, I will have to remove the lamina. So again, we will tie another twine. So we will have to tie it like that and again and allow it to come to equilibrium. So then again I will have to hold the ruler through this point. So here you can see it's in equilibrium and draw the line there. If we draw a line through that point, so here you can see all the three lines intersect through the same point. What do we call that point? That is called the center of gravity. So when you draw very thin lines, you can see the exact intersection. Now I have used the marker pen. So that is the center of gravity. We expect the weight of the object to act in that point. So that is what we call as the center of gravity. Now that we have found the center of gravity, what we will do is we will have to tie this lamina at 2 points, at 2 ends, and then we will need to hang it like a picture hanging on the wall. So we will need to tie it from these points. So we will have to hang the lamina sheet here. So these are the two forces, the tension acting along the strings. So then I will need to use another sheet of paper. Now what I will need to do is I will have to mark the two forces. So in front and mark the points from this side. And here. So this is how I got the points. Then I will have to draw the lines along the two strings. These are the two strings, two tension. Here you can see if I hold it this way, and here you all can see students, this is the center of gravity. So if we draw another line along the center of gravity, you can see that also will intersect these two forces. So as you can see here students, from the diagram, the two end tension acting along the string and the weight that is going to act downwards. So this is the weight that's going to act downwards and the tension acting upwards. All of them meet at the same point. So all of them are coplanar forces. As you can see, they are not parallel and also they all meet at one point. Those are the criteria that needs to be satisfied. In addition to that, you all will know that the sum of two forces will be equal to the third force. So those are the conditions that need to be satisfied in order to make an object under equilibrium under the action of three coplanar forces that are not parallel.